1958. So our next speaker is Armin from University of Vienna. And he's going to explain us a few things about nonlinear conditions for differentiability by almost analytic extension.
Thank you very much. Thanks to the organizers for inviting me and giving me the possibility to speak here. So as the previous speaker, Marco Abate, I have to apologize that there will be no dynamics in my talk and also no Transseries, but there will be a little bit of tameness and tameness in a rather unexpected place, I have to say. So let me start. Okay. Does not work. Maybe I can do it here. Okay, thanks. Okay, so I want to focus on a theorem of yours in the early 80s, which says that if we have any function real valued, and we know that the square of this function and the cube of this function is C infinity, then we can conclude that this function itself is C infinity. Okay, so this is rather unexpected, I would say. Let me make a few remarks. So first of all, what is M here? M is any C infinity manifold. Actually, for the proof, it's enough to consider M equal the reals. This follows from Bowman. So by Bowman's theorem, a function is of class C infinity if it is C infinity when composed with every C infinity curve in the domain. Okay, so that means actually, if you want to prove this, it's enough to consider M equal the real line. Okay, so Joris was not able to show this for complex valued functions. This was done a little later by Duncan, Krantz, and Parks in 1985. This is also true if F takes complex values, and it's even true if F takes values in a complex function algebra. Okay, I put here continuous. So just for safety reasons, so let us always suppose that F is continuous. It's actually not necessary in Joris theorem. The reason is that the cube has a global inverse. So the map T goes to T cube is a homeomorphism from the real line to the real line. So therefore, if you know that F cube is C infinity, you already know that F is continuous. Okay, but there are some easy examples which show that without continuity, general statements of this kind are not true. Maybe I will come back to that. So another thing is that the powers you see here, square and 3, are not really important. The important thing is that the powers are co-prime. So I could put here F to the power P and F to the power Q, where P and Q are two co-prime positive integers. Okay, and there, as proved in the paper by Duncan, Krantz, and Parks, there are more general nonlinear conditions. For instance, if you know that F squared plus F cube is C infinity, and any power of F is C infinity, then also you can conclude that F has to be C infinity. So let me point out that the condition that F squared plus F cube is C infinity is not enough. If this condition, the second condition, is not there, then you can find examples where you have that this sum is C infinity, but the function F is not C infinity. Okay. So this looks like a division result, right? Very simply because if you divide F cubed by F squared, you get F, naively. Of course, there's a lot involved here because a priori these are C infinity functions, so the 0z of the denominator can be very, very bad, okay? But the point of this talk is that there is a way to to make this naive idea into a rigorous proof. And this was proposed a few years ago by a user on Math Overflow, user nicknamed Fedia. He sketched a proof how to get this result in the C infinity setting by going to the complex domain and actually doing a division. Okay, and I would like to present this. And it turns out that this scheme of proof also works for other regularity classes, and I would like to present it in the context of Donjoua-Kaleman classes. Okay, so here is the theorem for other regularity classes. So I will show, just to warm up, that it is true in the holomorphic setting, in the real analytic setting, polynomial, Nash. So this is actually, we will see that this is very easy. And then I will focus on Donjoua-Kaleman classes, quasi-analytic and non-quasi-analytic. So it turns out that, so whether the class is quasi-analytic or not, does not really play a role here, which is also surprising. And let me just mention, maybe later on I will give some hints. This is not restricted to Donjoua-Kaleman classes. It is true for more general ultra-differentiable classes. Okay, and as I said, the key of the proof is to go to the complex domain. So we do this by almost analytic extension and then by holomorphic approximation. Okay. So first to the holomorphic setting. So, okay, first let me focus on the one-dimensional case. So the domain is just the complex plane. And let us suppose that we have a function such that the square of the function and the cube of the function are holomorphic. Well, then we can take the quotient h divided by g, and this turns out to be a holomorphic function except on a discrete set, because the zeros of the function g, they have to be isolated. Okay. Now we already have Lioris C infinity result, so we know that f is C infinity. So therefore, all the possible singularities can be removed, yeah, because the function is locally bounded, even C infinity in a neighborhood, and we are done. By the way, you do not need Lioris C infinity result in this context, because you can just compare the order of vanishing of the denominator and the numerator. Okay, it's very easy. And to go to several variables, you just use Hartog's theorem. Okay, real analytic. So here, from the start, I take arbitrary dimension d. Okay, and I take a complex valued function on Rd, and suppose that its square and its cube are real analytic. Well, then Lioris tells me that the function f is C infinity, and well, it satisfies an analytic equation, namely f squared is equal to g, and I know that g is real analytic. So by a result of Malgrange, I can deduce that f has to be real analytic, or you could also use Tam's theorem in this context, I guess. Okay. Polynomial, also easy. We already know by the holomorphic result that the function has to be entire, and then you look at the growth at infinity, you can control it because you have that g, for instance, is polynomial. And by Nash, for Nash, you just look at the defining equation. Okay. Okay, so let me now come to the main object of this talk. These are the ultra-differentiable classes, which are classes which sit between the real analytic class and the C infinity class, and they are given by bounds on the derivatives. So I will focus on the simplest case. So suppose we have a positive sequence M, which determines the growth of the derivative. So we consider the Donjoua-Kaleman class Cm on a on an open subset of Rd, and this is the set of all C infinity functions on this open set U, such that for every compact subset, we find a positive number rho, such that the alpha partial derivative of f on this compact subset K is bounded in a uniform way by alpha by rho to the alpha times alpha factorials times m alpha for all alpha uniformly. Okay, so in a sense, we take the Cauchy estimates and we perturb them, right? If m is equal to 1 constantly, then you just have the classical Cauchy estimates, and then your class would be the real analytic functions. Okay, and we we will also impose some standard regularity properties on this sequence M, which defines the class. We suppose that M is log convex, which is this condition for all K. We suppose that the roots mk to the power 1 over k tends to infinity. This means that the real analytic class is strictly contained in the class we are looking at. And we suppose that M has moderate growth, which is this condition for all J and all K. In particular, it implies that the class is closed under under taking differentials. Okay. By the way, I should stress that the log convexity condition also implies that our class has strong stability conditions. So, for instance, it's closed under composition, it's closed under taking inverse functions, it's closed under taking implicit functions. It's closed under solving ordinary differential equations. And but in particular, since the real analytic functions are contained, the closeness under composition also means that our class is an algebra. Okay. Examples. As I already said, if I take the constant sequence 1, I get the real analytic functions. If I take the sequence k factorial to the s, where s is a positive number, I get the Chevret class. These classes, as long as s is positive, are non-quasi-analytic. Here is an example of a quasi-analytic class. So here we have a log of k, then we multiply by log of k. We could go on, we could put also the factor log of k and so on. The last factor gets a power which is strictly which is between 0 and it might be 1, and we take the kth power of the whole product. Then we get a quasi-analytic class. Quasi-analyticity can be characterized by this summability condition here. This is the Donjoy-Carleman theorem. Yeah, let me repeat, but although I think that everybody knows here that quasi-analytic means that Taylor expansion is injective on every connected component of the domain. Okay. Well, so I will focus on this Donjoy-Carleman classes, but let me tell you that there are many more ultra-differentiable classes which were studied classically. So for instance, I could replace this existential quantifier by a universal quantifier, and I would get another class. I will not talk about it here, but everything I'm going to do is also true for these variations. Yeah.
These are the classes, these quasi-analytic cohorts.
It's the same. So the characterization is just the same. Okay, so there is a recent result by TA, and he showed using the sketch of proof of Fedja on math overflow that in one dimension, so the domain is just a real line, a function which has two co-prime positive powers which are in the Donjoy-Carleman class Cm, has to be actually also in the class Cm. Okay. So so this is a theorem in 1D, in one dimension. So there are possibilities to go from one dimension to higher dimension, analogous to the C infinity case, but this works only in the non-quasi-analytic case, and only for the classes we are studying here. For instance, if I would put the universal quantifier in my definition, this is rather unclear, and I doubt that this is true. But for non-quasi-analytic Langevin-Kalemann classes, as we have it here, there is a version of Bowman theorem, so you get immediately the multidimensional result. Okay, but for quasi-analytic classes, this is not true. Okay, so it's actually not clear if you have this result how to go to many dimensions. But we could manage to do that in a recent in two recent papers. So actually, this theorem remains true for all, I put here reasonable, ultra-differentiable classes in all dimensions, no matter if quasi-analytic or not. What do I mean by reasonable? I mean that I have to impose some conditions on the weights which are involved, right? Okay. Yeah. So how to do this? Okay, I will go to the complex domain and try to divide in the complex domain. So how to do that? I need a function which is associated to my weight sequence M. I denote this function by HM, and it's the infimum over all non-negative integers of the terms mk times t to the k. Okay, if t is positive, if at 0 I just put the function equal to 0. Okay, so it's not hard to see that this function has the following properties. So first of all, it's increasing, it's continuous. So in particular, the limit at 0 is 0. It's positive, strictly positive for positive t. It becomes 1 for large t. So more precisely, for t greater than 1 over m1, it's equal to 1. And it's infinitely flat at 0. So actually, it's not hard to see that you have the following expression for hm. So hm is given by this, actually by this monomial, if t lies between these two quotients, mk over mk plus 1 and k minus 1 over mk. Okay, so from here you in particular see if you approach 0. By the way, these quotients are tending decreasingly to 0 as m goes to as k goes to infinity. So this says that in particular the function has to be infinitely flat at 0. Right? So okay, so here are a few examples. For the constant sequence 1, it's not hard to see that the function is identically 0 on the interval 0, 1. Okay, I said the function is always positive for positive t. This is, so strictly speaking, this case is not covered because, why is it not covered? Because I had the assumption that mk over 1 to the power 1 over k tends to infinity. But here mk is just 1, so this assumption is not satisfied. Okay, but anyway I put it here because this would be the real analytic case. Okay, so this is a quasi-analytic weight. Here the h function has is comparable to this double exponential function. So you see it is very flat at the origin. For the Chevret case, it is an exponential function, also flat at the origin, as you see here. All right. There is the following theorem of Dynkin, proved in the 70s. You can actually characterize your class in the following way. So a function f is in your Langevin-Kalemann class Cm, on the real line if and only if for each compact interval I, there exists an extension of the restriction of the function to the interval I to the complex domain, which is C1, and suppose that it has compact support, such that the d bar derivative of this extension f satisfies this bound. So it's bounded by a constant time the function hm with the argument another constant rho times the distance of the point C to the interval I. So, and this is true for every C in the complex plane. Okay, so you get this characterization of the Donjoa-Carleman class Cm in terms of what we call almost holomorphic extension. So, for instance, a real analytic class is precisely the class where here the right-hand side is 0. So it means that the extension has to be holomorphic, which is, yeah, classical. Okay. Let me mention that if my class satisfies, suppose that I have a class, not necessarily a Donjoa-Carleman class, which in some way admits such a representation, then it automatically has good stability properties. For instance, stability under composition, stability under ODE, stability under implicit functions. Why? Because it's easy to show this using this sort of condition. And it's actually easier to show it as for the usual definition, because you have to control only one derivative instead of infinitely many derivatives all at once. Okay. I should also mention that there is also a characterization of this type of the C infinity class. In this case, you would here need that this d bar derivative of the extension goes to 0 faster than any power of the distance to the interval. Okay, so but this was used in the proof of Malgrange preparation theorem by Nierenberg, for instance. Okay. Now, okay, we have now almost holomorphic extension to the complex domain, but we actually want to deal with holomorphic functions. So we will modify it to get holomorphic functions. And we will do this on special domains, which are ellipses. So for every epsilon, I take omega epsilon, the interior of the ellipse in a complex domain, which has vertices hyperbolic cosine of epsilon and plus minus I times the hyperbolic sine of epsilon. So it looks like this, and notice that the interval, the unit interval -1, 1 is always contained in the interior of this ellipse. Okay. And there is the following result. So suppose we have a function in our class. I restrict it, so I suppose that the function lives on a unit interval, and it's the closed unit interval. So actually, formally, I did not define this, but it means that the bounds are valid globally on the whole interval. Okay, so the defining Donjoa-Carleman bounds hold uniformly on the interval -1, 1. So if I have such a function, then I can find a family of functions f epsilon, which so each f epsilon is a holomorphic function on the domain on this interior of the ellipse, omega epsilon, continues up to the boundary of the ellipse, such that, well, it's uniformly bounded. So this is my notation for the subnorm of the function. It's uniformly bounded on the ellipse, and on the on the unit interval, it approximates the function f in terms of the HM function, the associated function of my weight. Okay, and this is true for all small epsilon. So the constant C1 and C2 work for all epsilon, so they are uniform in this respect. Okay, so let me sketch why this should be true. Okay, so by the almost holomorphic extension theorem, I know that my function in the class Cm allows almost holomorphic extension, capital F, which satisfies this condition. Okay. Now I take the d bar derivative of f and I cut it off outside of the ellipse. So I multiply it with the indicator function or characteristic function of the ellipse. So I put it 0 outside. Okay. And then I take the convolution of this function, which with the Cauchy kernel, yeah. Then this is this new function v epsilon is a bounded continuous function which solves the d bar equation where the w epsilon is the right hand side. It solves it in a distributional sense. Okay, and then I take the extension capital F and subtract this solution of the d bar equation, then by the very fact that this function solves the d bar equation, the function I get, f epsilon, has d bar equal to 0 in the interior of the ellipse. Therefore, it's holomorphic. And then it's an easy exercise to show that it also satisfies the other properties here. Okay. Okay, so that means if we start with the Donjoy-Kaleman function, we get such a holomorphic approximation, but that's not enough. We also want to come back. Okay, so to come back, we have the following. So suppose we have any function defined on the unit interval and values in C. If there exists a holomorphic approximation as specified before, so we have these ellipses, we have uniform bound on the ellipse, we have uniform approximation of f on the unit interval in this way, then I state that f has to be an element of the corresponding Donjoy-Kaleman class in the open interval -1, 1. So I lose a little bit, but that's not important for me. Okay. So by the way, I forgot to tell you that. So I mean it's clear, but notice that also the domains of these functions, well, they shrink if epsilon goes to 0. Right? They shrink to the interval -1, 1. Okay. Let me give an idea why this is true. So, okay, now we are given this holomorphic approximation. So I take f epsilon minus f2 times epsilon and call it g epsilon. This, of course, is a function which is holomorphic on the ellipse omega epsilon up and continues up to the boundary, right? By the triangle inequality, g epsilon satisfies this uniform bound on the ellipse, and we have that this uniform bound on the unit interval. Okay, so what I want to do next is get a bound of this type, not only on the unit interval, but on an ellipse, on a whole ellipse, which is, okay, it has to be smaller than the one I start with. But anyway, an ellipse, okay? So, and this can be done by Habermas' 3 lines theorem. So I get, the upshot is I get a bound of this kind, where on the right-hand side, I have the function hm on an ellipse, and to be precise, it's the ellipse omega epsilon half. Okay, so how this is done is the following. So notice that, so here is the ellipse omega epsilon, and this ellipse is the image of the strip in the complex plane of all points with whose imaginary part has absolute value less equal 1, or strictly less than 1. Under the map, z goes to the sign of epsilon times c. Okay, so this map is surjective onto the ellipse. It's highly not injective, but that's not a problem for me. Okay, and so I have the function g epsilon, which lives on the ellipse. I pull it back by this map. Now I have a function which lives on this strip, and I can apply Hadamard's 3-line theorem. And I see if I do that, I will not go into details, but I see that if I go to the strip of all complex numbers whose integer part has absolute value less than 1/2, then I get this better bound. Okay, and this is if I go back to the ellipse, this is precisely under this map. This the image under this map is precisely the ellipse omega epsilon 1/2. Okay, and then in the next step, remember we want to show that our function satisfies Don-Joua-Kaleman bounds. So I look at the derivatives of g epsilon, derivatives of all order, and I take a strictly smaller, so I take any number less than 1, and I look at the corresponding interval minus b, so this number is called b, and I want to bound the derivatives on this interval. Okay, so I do this with the Cauchy estimates, and I have to make sure that I do not get out of the ellipse omega epsilon 1/2 in order to use these bounds. So here what you see in the denominator is an absolute constant e times 1 minus b times epsilon. And this is, so here I'm using that I can find an absolute constant e such that the disk, which is centered at any point in the interval minus bb and has radius e times 1 minus b times epsilon, lies still inside this ellipse so that I can use the bounds. Okay. Well, then the epsilon I have here, I can, so actually I have epsilon to the k in the denominator. I can absorb this in the function hm because I assume that my weight sequence m has moderate growth. Okay. The cost I have to pay is that I get the factor mk in front. Then what remains here is just a number, so I call it sigma, and then I can divide by sigma to the k times k factorial times mk, and I get a defining seminorm for my class. Yeah, I put it here. And since I still have this hm on the right hand side, and hm goes to 0 as epsilon goes to 0, I see that this sum here converges in the norm topology with respect to this norm. Okay, so it gives me an element actually in this space where you have to you have to replace here the interval by this interval, by the interval minus bb, and you can take the closed interval, right? So I get a function in the right space, and look here. So the j I have here, I could actually put any integer, positive integer j here, because this is a telescoping sum. Okay, so in the end, I can also let the j go to infinity, and this shows me that this function g actually coincides with the function f with which I started on the interval minus bb. Okay, so it means that actually the function f is an element of this Donjoy-Kaleman class, as I claimed. Okay, so now we have these two theorems. We can so we have, in a sense, a description of Donjoy-Kaleman classes on the real line by holomorphic approximations, and we are going to use that. So let me briefly describe the strategy of the proof of Joris theorem for Donjoy-Kaleman classes. Okay, using all the ingredients I've been talking about now. So I recall that what we want to show is that if we have a function on the unit interval with complex values, such that the square of this function and the cube of this function is in the Donjoy-Kaleman class on the unit interval, then the function itself has to be in the Donjoy-Kaleman class. Notice, so here I have Donjoy-Kaleman class up to the boundary. Here I have just the open interval, but this does not matter because the statement is local, so it's not an issue.
Here you are just assuming continuity.
Here I don't use it, so I think I don't need it. But for safety, you can think that f is continuous. Okay. Right. Okay, so I will sketch several steps. So the first step is the first holomorphic approximation theorem. So we start. So I call f square, I give it a name, it's called g, and f cube, I give it the name h. Okay, so I use the first holomorphic approximation theorem to get holomorphic approximations of g and h. So they are called g epsilon, h epsilon, with all the properties we have been discussing. Okay. Next step, I want to divide. So actually what I want to divide is h epsilon by g epsilon, right? Because h epsilon is close to cube of f and g epsilon is close to square root of f. And I want to get f, right? For technical reasons, I have to look at a more complex complexly defined function. Okay, so I look at this function u epsilon, which is this guy here. So for here, the r epsilon is a suitable positive number, which depends on epsilon. And suitable means it has to depend in a specific way on epsilon. It actually has to involve the function hm of epsilon in some way, right? Because in the end, we want to have such estimates. And on the right-hand side here, we need hm appearing, okay? So this is rather delicate. The function phi epsilon you see here in front is a cutoff function. So it's a C infinity function which has support in the ellipse omega epsilon, and it's equal to 1 on the smaller ellipse omega epsilon half. Okay, so this is also just for technical reasons. And then we have this expression here. So we have g epsilon bar. The bar means, of course, the complex conjugate times h epsilon, and in the denominator we have the maximum of the modulus of g epsilon squared and this r epsilon squared. So notice that if it happens at those points where actually the modulus of g epsilon dominates this number, yeah, so that means the maximum is just the square of the modulus of g epsilon, then actually this quotient here is just the quotient I want, h epsilon divided by g epsilon, okay? Okay, so this is a function which is continuous, bounded. It's not holomorphic, of course. Okay, but one can show that it has the right behavior. So it's uniformly bounded on the ellipses, and on the unit interval, it approximates f in a certain way. As I said, this r epsilon involves in some way the function hn. So this is good. Okay. Epsilon is small for all small epsilon. For all small epsilon. In the end, we want. So it's written here. Yeah.
If it is very small, you will smaller than g epsilon. But you cannot.
Yeah. Yeah. No. It's more complicated than that. Anyway, so what is still missing somehow is that this function is not holomorphic. Okay. So the next step means we want to make it holomorphic. So we want to modify the function u epsilon to get actually a holomorphic approximation f epsilon of the right kind, because then we know already, then we can go back. Okay, so this is another application of solving the d-bar equation in a clever way. Okay. But then we have to show that once we do this, we modify u epsilon in a clever way to get a holomorphic approximation. We have to show that this approximation actually has the right properties. Okay, so if we manage to show this last line, then we can use the second holomorphic approximation theorem to get back and conclude that f is in the Donjoy-Kaleman class as we want, right? So to show, so the step 3 involves a very delicate analysis of the d-bar problem that you solve here. Okay, good. So let me go on. So so this was a sketch of the proof in one variable, as TA did it. So we can actually go to many variables. So this is in our work. So the result, your result, is true in Donjoy-Kaleman classes in any dimension. And so it's even true for more general ultradifferentiable classes. And it turns out that the proof does not only work in any finite dimension, it even works in arbitrary infinite dimensional Banach spaces, and you can even go beyond that. So it works even in suitable locally convex spaces. Okay. And we also get a uniformity result. So in the following sense, so the map which takes f to the pair f to the power p, f to the power q, I recall that p and q are co-prime positive integers. This is an injective map from the set of all functions from Rd to C to the product of this set with itself, right? This is an injective map. So I can look at the image and I get the inverse on the image. And this inverse, so this is actually solving or actually going from the pair fp, fq back to the function f. This map takes bounded sets in this product of Donjoy-Kaleman classes to bounded set in the Donjoy-Kaleman class, bounded with respect to the natural topology you put on this set. Yeah? So let me not go into that. Okay, so let me give you 2 words on the proof. So for the proof, one ingredient is the polarization inequality, which says that I can control the Fréchet derivative of a smooth function right, of any order by the directional derivatives. If I have directional derivatives of all orders and in all directions. Okay, so actually, and if I have Fréchet derivatives, then automatically I have all information about the partial derivatives clearly. Okay, so actually it's enough to study directional derivatives uniformly. Okay, and this is precisely what we do. So so it turns out that a function on Rd is of class Cm if and only if all the functions, all the restrictions of f to line segments at all points and in all directions admit uniform holomorphic approximation in the following sense. So I find a family of function f, which now depends on x. So x is the start point. Here v is the direction, which now depends on x, v, and epsilon on these ellipses, such that these bounds are satisfied. Important, these bounds have to be satisfied uniformly in all x and all v, and of course for all epsilon small. Okay, and with these two ingredients, you go into the proof I presented you. You check that everything we did, actually I just only gave you a glimpse of the proof, but you have to check that every bound is uniform with respect to x, v, epsilon. And then you get it automatically, then the proof gives you the result in many dimensions, even in Banach spaces. Okay, so in the last part of the talk, I would like to speak about more general nonlinear conditions. So I can rephrase what I told you about in the following way. So now I'm looking at germs because anyway, everything is local actually. So I take a continuous germ defined in a neighborhood of 0 in Rd, and it takes values in R or C, does not matter. Okay. Then we know Joris' theorem tells us that if phi composed with f is in the class, then f is in the class, where for now we studied the germ phi of t is t power p comma t power q, where p and q are co-prime integers. Okay, so it's natural to ask that what other analytic germs have this property. Okay, let me call this property PM. By the way, it was also studied by Joris and Preissmann, and they called it in the C infinity setting, they called it the property of being pseudo-immersive. Okay, so so let me give you a necessary condition. Okay, so since I look only on analytic germs, I can expand them in a power series, right? Here I write down the power series in such a way that only terms which are non-zero appear here. So the nk you see here in the powers, they are, so the set of all nk is actually the support of this power series, yeah, and it takes values in kn and the 0 is included. Okay, now I will show you that this phi has property Pm. If it has property Pm, then the greatest common divisor of the support has to be equal to 1. Okay, so that's the necessary condition I'm talking about. In fact, suppose not, well, then they have a common factor P. Okay, I can look at the power series psi, where now I take the powers Lk instead of the Nk. This is convergent, of course. And it turns out that phi of t is psi of t to the power p. right? But of course, I can easily find a continuous germ F, which is not even C1, whose composition with this guy here is analytic. So take just the pth root of T, for instance, right? So yeah, so this is a necessary condition, and it turns out that it's also sufficient. But first, for the statement, let me introduce first what I mean by equivalent germs. So I have two analytic germs, and I say that they are equivalent. If I can find analytic diffeomorphisms such that if I pre-compose and post-compose with this analytic diffeomorphisms, I get from one germ to the other germ, okay? And it's easy to check that equivalent germs either both have this property or they both do not, right? And then with this equivalence relation, it's actually no restriction to assume that the first component of my map, of my germ, is equal to a power, okay? And now the statement, suppose we have an analytic germ defined in the neighborhood of 0 in K with values in Kn. The first component, as I said, is a power T to the P, and the support of the power series, which defines this germ. Yeah, the statement is this germ has the property to be pseudo-immersive in the Donjoy-Kaleman class if and only if the greatest common divisor of the support is equal to 1. Okay, so in the C-infinity setting, as I said, this was studied by Joris and Preissmann, and in this case, they treat C-infinity germs. In case that we are in the complex domain, then you have to ask that it has a complex Taylor series, right? And the characterization is just the same in the C-infinity setting. Okay, so just very quickly the idea of the proof. So first of all, the power can be assumed to be greater or equal than 2, because if it is 1, we are done. Okay, and n can be assumed to be equal to 2. In fact, I can find real numbers gamma I such that this pair consisting of only 2 function has the property that the support has greatest common divisor equal to 1. So I restrict to n equal to 2. And the idea then is to show that I can find a positive integer such that t to the power 1 plus p times q can be represented as a polynomial in this guy, phi of t, with coefficients, analytic germs in t to the power p, right? And if you have that, then you're done, because now I plug in the function f instead of t, then by assumption, phi of f is in the class, and t and f to the power p is in the class. So this, since I have stability under composition, I know that this power is in the class, and then I just use Joris because I have 2 co-prime powers, right? Okay, let me end with, yeah, you have uniformity as before. Let me not go into that. You are also close to necessary. In fact, you're necessary. I mean, the conditions on M are, you cannot improve much. That's my point here. Let me not go into that too much. I want to end with a few examples. So now we actually are able to understand the example I had on the first slide. So this is even true in the Donjoy-Kaleman setting. So if f squared plus f cubed is Donjoy-Kaleman, and I have a power of f which is Donjoy-Kaleman, then f is Donjoy-Kaleman. because you just have to look at this support of the powers which appear here, and they have to have greatest common divisor equal 1, of course. So we can apply the theorem. Let me give you a few limitations of the theorem. So we cannot go beyond complex function algebras in general. So here is an example. If you look at the Banach algebra, which contains a non-zero nilpotent element of order 2, you are doomed, because I can then just define f of t. T is a real variable equal to x. So this is this element. If t is a rational and 0 otherwise, this is highly discontinuous, but the f squared and f cubed are equal to 0, so smooth, right? This is rather pathological, but there is another example. Let us consider the algebra of 2x2 matrices of this type, say with the Euclidean norm. And then I put a of t is a flat function at 0, and b of t is the absolute value of t. And I look at this function here, right? This is a function which is continuous but not C1 because of this guy, right? But the square, if you compute, it looks like this. And here, the flatness of this factor makes the square flat. And the same for the cube. So f square and f cube are C infinity, although the function itself is not C1. And to finish, Joris' theorem is also wrong for the quaternions, right? So the quaternions can be written in this form. So they can be represented as 2x2 matrices with complex entries. So Z and W is a complex number. You have Z, W, and you have in the lower row, you have minus W conjugate, Z conjugate, right? And then let me look at this function, right? And if you compute the square, it turns out to be this expression. If you compute the cube, it turns out to be this expression. You can find a function W of t, which is not C2, but all the guys which appear here in the square and in the cube are C infinity. Okay, so this is another limitation. It's not true for quaternions. Okay, thank you very much.
Thank you.